This unit looks at multiple regression. Multiple regression is based on Pearson's R correlation. But instead of having an independent variable and a dependent variable, you have a dependent variable and multiple independent variables. Basically, you're looking at the combined effects of two or more independent variables on a dependent variable. R, similar to R, is a PRE measure when squared. Meaning, just like with Pearson's R squared reveals the proportion of the variation in the dependent variable that can be explained by the combined effect of the independent variable. Just like with bivariate correlations, linear multiple regression is based on the idea of a line, except in this case, the formula is expanded. Y, the dependent variable, is equal to A, the y-intercept, the point at which all of the independent variables' value would be 0, plus the beta for the first independent variable times that variable's value, plus the beta for the second independent variable times that variable's value, and so forth. What are the assumptions of multiple regression? In this case, you're going to have an interval ratio or scale level dependent variable. You'll have two or more independent variables. There should be independence of observation, meaning the observations are independent of each other. It should be a linear relationship. Homoscedasticity, or finite variance. The variance within each of the independent variables should be finite. There should be no multicollinearity. The independent variables should not be correlated with each other. There should be no significant outliers, extremely high or extremely low values, likely to affect the distribution. And you want a normal distribution of residuals or error. There shouldn't be a pattern to the error. In lab, you'll have an opportunity to try your hand at linear regression. We'll be using the Analyze Regression Linear command. Make sure you select stepwise regression as is specified in the course lab book. The beta coefficients for each independent variable tell you its effect on the dependent variable. The further away they are from 0, the stronger an impact they're having. With multiple regression, you might get multiple models. Using the stepwise command, it'll eliminate any of the variables that aren't statistically significant and give you back the variables in the order of their strength. Also note that you'll be given the value of R. R is the square root of R squared and is the correlation between the observed and predicted values of the dependent variable. R squared is the proportion of variance in the dependent variable which can be explained by the independent variable. This is an overall measure of the strength of association and does not reflect the extent to which any particular independent variable is associated with the dependent variable. The adjusted R squared penalizes the addition of extraneous predictors in the model. The standard error of the estimate is referred to as the root mean square error. It's the standard deviation of the error term, or how spread out the error models are. For the purposes of this class, focus on understanding what R and R squared are telling you about this model. The constant is the y-intercept, or the height of the regression line when it crosses the y-axis. This is when all the predicted values of the other variables are 0. B are the values of the regression equation for predicting the dependent variable from the independent variable. A common way to express the regression equation is listed below. Y predicted is equal to the constant plus the impact of each beta on each independent variable. The standard errors are those associated with each coefficient. How far off is our estimate likely to be? The standardized betas listed in the output table that you'll see standardize all the coefficients onto the same scale. In the original regression equation, they're in the units of that particular variable. So for example, age is in years, whereas income would be in dollars. The standardized units put them all in the same scale so you can compare their effects. Lastly, the T and SIG columns give you whether or not that particular variable is statistically significant in your equation. As in other tests of significance, what you're looking for is in the SIG column is p less than 0.05. Dummy variables allow you to include nominal and ordinal or categorical variables in multiple regression equations. Dummy variables are placeholder or indicator variables that allow you to have a two-category presence-absence yes-no represented through 0, 1 for a particular characteristic. For gender, this is an easy example. 0 is female, 1 is male. That shows us the effect of being male. What if you had something like race? Well, you could still create a series of dummy variables such that you could have a variable black, where 1 is the effect of being black and 0 not black. And then Latino, 1 is Latino, 0 not Latino. If you're creating a dummy variable like this, you'll always want to leave out or not include a final reference category. So if I'm comparing all of these things, I wouldn't include white as a dummy variable. I've already seen the impact of being white. Here's an example of how you would recode to create a dummy variable for gender. In the original survey, female was 1 and male was 2. I constructed a dummy variable of male to look at the impact of being male, making male 1 and female 0. There weren't enough transgendered people in the sample to allow us to do any statistical analysis of that group. Here is an example of multiple regression output. In this case, the dependent variable was texting. It was a total number of texts the individual sent over a particular period of time. Predicting how much one would text was age, measured in years, a dummy variable for male, and income. When we take a look at this table, what we see is that the overall model, as shown in the first table, is statistically significant. P equals 0.000. What we see when we look at our model here, though, is that age is having a statistically significant effect. For each year one goes up in age, one's number of texts sent goes down by 0.441. The dummy variable for male isn't quite statistically significant at 0.066, with a negative 4.090, which would indicate that being male means you send about 4 less texts a day. However, it's not quite significant. And as we can see, income isn't significant at all. P equals 0.644. So if I were trying to predict the number of text messages you would send, I would start with the constant, 26, and then I would take your age and multiply it by 0.441 and subtract that amount from 26. Even though it's not significant, I'd probably guess if you were male about 4 fewer texts. Here's a final example. In this case, I decided to predict texting using age, since I already saw that was having a statistically significant relationship. The dummy variable for male, I wondered if I put it in an equation without income if it would become significant, and one score on the self-esteem index. What I can see here is that age and the dummy variable male in this case are both statistically significant, and self-esteem was actually pretty close. I'm wondering if with the larger sample I might not achieve statistical significance. In this case, I would predict the number of text messages one sent based on, I would start with a baseline of 19.336, then I'd take your age and multiply it by 0.394 and subtract it from there. If you're male, I'd subtract 4.874 text messages, and then I'd take your score on the self-esteem index and multiply it by 0.388. Remember, the higher the score, the lower your self-esteem. So people with lower self-esteem are texting just a little bit more, according to this model. Though remember, self-esteem is not truly statistically significant.